So this is a very simple equation, right? The change in a system is equal to the current value minus the prior value. And despite being very simple, it's going to be the basis for a lot of the work we do over the next several lectures. We're talking about methods for modeling both the change in the system and ultimately back to the system itself. So just kind of file this away. Right, we're going to come back to it frequently throughout the next couple of lectures. So we're going to start off with some terminology here. A sequence is something you've probably already seen already. You're likely accustomed to thinking of a sequence as being just a list of numbers. And that's fine. That's what it is. And our definition isn't going to change that. It's just going to make it a little more formal. We're going to say that a sequence is a function from the positive integers. Those are the numbers 1, 2, 3, and so on. Sometimes we'll throw 0 in there, right? That's fine too. To the real numbers. So these positive integers, these are the indexes here, the n values. And the function just tells us what number is assigned to each step in the sequence. Now, we want to talk about change, right? So we're going to define the first differences of the sequence to be the difference of a pair of consecutive values. So delta A sub 0 is the 0 value, the initial value, minus A sub 1. Delta A sub 1 is A sub 2 minus A sub 1, and so on. And then you've got kind of the general term down here. The thing you need to keep in mind here, and this always, I still have to stop and think about this sometimes, is that the index of the delta value is equal to the previous number, not the current number, right? So just kind of, just every once in a while, you might need to stop and remind yourself of that. And in general, delta A sub n is called the nth first difference. Okay, so that's great. Now we've got some definitions here. Let's look at some specific. So before we get started, if you're taking notes and copying this table down, leave room for a fourth column. Right, I'm going to add one on the right-hand side there when we get about halfway through. All right, so when I'm looking at a new concept, one approach I like to take is starting with an example that I'm already familiar with. Right, that helps me to just focus on the new concepts rather than having to think about the details of the scenario. And it helps me to confirm that my understanding of the concepts is correct, since I already have an idea of what the results should be. So what I've got here is data for the sample size of a decaying radioactive isotope. Measurements were taken every hour, and these numbers in the second column are the results. Now, you may already know that radioactive decay can be described using an exponential model, but what I want to focus on here is the change in the sample size and what that can tell us. So first, let's think about how the data fits into our idea of a sequence of numbers. The interval numbers here will be the n values, and the sample sizes will be the A sub n values. That makes the changes delta A sub n. And you can see this would be delta A sub 0, and that is A sub 1, 70.71, minus A sub 0. All right, so this fits into the definition. Okay, so again, we're referring back to those definitions. These values in the third column, negative 29.29, negative 20.71, negative 14.64, etc., those would be the first differences. Okay, so where this gets interesting is if we go one step further and calculate the percent change. We take each change value and divide it by the previous sample size. Right now, you're welcome to pause. That's going to be my fourth column here. You're welcome to pause and do those calculations for yourself. If you want to see for yourself what's going on, then you can start this back up and see my results. Okay, so if you do those calculations, you should see this result. Okay, obviously those are the decimal values. There's no percent sign. Those are the decimal values, all right, not the actual percentage. So it would be negative 29.3%. Right, but I'm going to stick with the proportions, the decimal values, because we're going to do some arithmetic with them here. All right, now things are starting to get interesting. Despite the fact that the total size of the sample is changing at a variable rate, the percentage by which it's changing is constant. Right, so how can we model this? Right, that's our ultimate goal here. How can we model this analytically? Well, let's start with the definition of percent change. That's delta A sub n divided by A sub n. Okay, and this equals the percent change, which is a constant. It's negative 0.293. All right, so let's see if we can work with this a little bit here. Let's clear the fraction. Delta A sub n is negative 0.293 times A sub n. And then, let's see, delta A sub n. You remember our definition, right, from the previous slide? This is this is just A sub n plus 1 minus A sub n, still equal to negative 0.293 A sub n. And now, finally, let's add A sub n to both sides, right? Because I see I've got one on both sides. If I do that, I get A sub n plus 1 equals 0.707 A sub n. All right, this equation, together with an initial value, for example, A sub 0 equals 100, gives us what's called a dynamical system, or a dynamical system model. Right? This gives us an algebraic analytic formula that describes the state of this system, the size of the samples over time. Okay, so this discussion leads us to some new definitions. Right? A difference equation is just an equation that tells you the next value of a sequence, right? That's the n plus 1, in terms of the previous value and possibly that value's position in the sequence. Now, what makes this a first order difference equation is that we only need to know the value of the previous term in the sequence to calculate the next one. All right, so looking back at our previous example, f of n comma y sub n, this function here, would be 0.707 y n minus 1, right? 0.707 times the previous weight. Right. Now this I will admit is always a little counterintuitive to me, since this equation doesn't mention differences anywhere. But just remember that to get to this point, we started off with information about the differences between the two values, then simplify that result to get this kind of formula where we hit solve for one of the variables, right? Which is kind of what we usually do to make it usable. All right. Now, if you go online and look up dynamical system, you'll see a lot of definitions. Some of them get very technical, involving things like measures, phase spaces, ergodic theory. And those are all great. And a lot of fields have their own very specific definitions based on the things that they're interested in. Right? This definition expresses the main goal of a dynamical system, regardless of the field. It's a way to describe the way a system changes over time. And that's what you saw with our final difference equation here, right? As time goes on, we can calculate the successive weights of the sample. All right, so I have a few additional observations I want to make before we move on. First, difference equations are iterative, right? Remember our formula. It was a sub n plus 1 equals, what was it, 0. See, now I've forgotten what the percentage was. It was 0.707 a sub n, right? So to find a sub n plus 1, you have to know a sub n. In other words, to find the time, the value a when n equals 100, you have to know the value when n equals 99. To find the value when n is 99, you have to know the value when n equals 98, and so on, right? So this is different from the functions that you're used to seeing, that you're probably used to seeing. Those functions let you just jump in anywhere. You pick a value for x, doesn't matter how big or small it is, you drop it into the function, do a little simplifying, get your calculator out, and you get the new value. Right? These difference equations are not like that. You can't just jump in at some random spot and find the value at that time. They don't have to be based on exact values. Now, I know that what I did here, I calculated those numbers exactly using the half-life of and so forth. Obviously, sometimes, a lot of the time when we're dealing with real-world models and real-world data, it's not going to be exact, and that's fine, right? Again, we're looking at kind of a streamlined example here. In later lectures, we're going to take this a step further and see how we can apply this to the kind of slightly irregular data that you get from experiments. And finally, our difference equation here was linear, right? The a sub n plus 1 equals 0.707 a sub n. That is a linear equation. But clearly that's not a requirement. And we will shortly here be looking at some examples of some situations that are nonlinear. Okay, so that was a good starting point, right? We've seen an example of a physical system that can be modeled with these new difference equations of ours. In the next lecture, we're going to take this a step further, and we're going to look at some additional relationships here. We're going to start looking at things graphically. There's going to be a lot of graphing that we do throughout this class. And that's going to help us down the road when we start looking at that experimental data where the numbers that we're getting maybe aren't always exact.